Alright guys, welcome back. Today we're going to talk about two more basic circle theorems. We saw two from yesterday, and today we're going to look at two more. The first one is called radius tangent theorem. It's basically saying that if you have a tangent that passes through the circle, like this line over here, okay? And first of all, we know that there is only one point over here. But then the second thing is, what this theorem tells us is, if you go from this line all the way to the center of the circle, guess what? This line is actually perpendicular. So OAT in this case, or OA, the other end, they're both equal to 90 degrees. Okay, so that's very useful later. Let's look at the second one. The second one is, if we have tangents, two tangents from a point, an external point. I'll probably give this theorem a short name called tangent external. How about that? Okay, that's basically saying that if we have one external point over here, outside the circle, okay, such that we're making two tangent lines, like this, then, surprisingly, for some reason, in this case the PB and PA, they're the same. Okay, so basically one point, if you're making two tangent lines towards the circle, the distance are exactly the same. And that's it for today's theorems. Now before going for the examples, here's an overview of all basic circle theorems. We've gone over 4 so far. The first one I'll probably call a semicircle theorem. The second one I will say, it doesn't really take much effort to write the full name, course of a circle. Third one, it's pretty short already, radius dash tangent, or tangent radius. The last one I'll probably call that the tangent external. How about that? And I think that shortened things so much already. So let's take a look at examples. Now first example, we need to find A and B. Right, A is very easy to find. First of all, we need to claim that AP has to be equal to BP. Right, this is because of the tangent external theorem that we looked at just now, and that because AP is equal to 7, BP is absolutely 7 as well, so that solved the problem. And let's look at part B. Part B is a little bit hard to deal with because the first thing that we need to know is OBP is equal to 90 degrees. Okay, why do we know that? It's because of the tangent radius theorem. Okay, and that means if you have a 90 degree over here, we can use a trigonometry of a right triangle, right? So imagine that this is your angle B, and then here's your opposite. Your opposite is A, but A is equal to 7, we solved that already. And here is your adjacent over here. We have opposite over adjacent. What does that remind you of? Yes, that's tangent. So tangent B is equal to opposite 7 over adjacent 3. Okay, how do we solve for B? B is equal to inverse tangent, okay, tangent minus 1, of 7 over 3. Okay, if you solve that, punch it into your calculator, you're going to get 66.8 degrees approximately. And that's it for this question. Alright, part 2. Again, we're not given any diagram, so we should produce one by ourselves. This question is phrased a little bit confusingly. Okay, so let's read through that together. The tangent from point M to a circle of radius 5 is 12 cm long. Okay, so we have a circle of radius 5, that's what we know. Okay, so that's 5 over here. But what is 12? They're basically saying this. Okay, so if you have an external point over here outside, okay, this is a point M, and then you're making a tangent line from this point, right, a tangent from point N to a circle. Okay, so you're making the tangent line from point N to a circle. Okay, and that length over here, that tangent line over here is 12 centimeters long. That's basically what the question is about. Okay, and we need to use that to figure out the distance from M to our center O. Well, that's pretty easy, eh? First of all, you just need to say that OAM, okay, let's call this point A. OAM has to be 90 degrees because we have tangent radius. So that gives us 90 degrees over here, and that makes the whole problem so easy. Because all we need to do is just use Pythagoras theorem. And that's equal to 5 squared plus 12 squared. Some of you probably don't even need to do that calculation. You will know the answer is 13 centimeters. And that's it for this question. Let's look at a not so typical question from your textbook. We have a circle. We have 4 tangent lines constructed. So you see 1, 2, 3, 4 points of contact. Okay, especially given the fact that they are all tangent lines. So we can actually name that in this way. If this is W, this has to be W, right? Because of the tangent external theorem. Right? Here's an external point. Distance should be all the same. Okay. Same thing. If this is X, this one has to be X. Okay. We can keep going, right? This is Y and this is Y. And lastly, if this is Z, this has to be Z. Okay. So we'll basically just put one sentence over here to explain everything. With tangent external theorem, we have W, X, Y, and Z as shown, and that explains everything. Okay, so let's start out with the left-hand side. The left-hand side is AB plus CD. This is what we're trying to prove, right? But we don't know whether they're equal, so we cannot assume that they're equal. So what we're going to do is we look at them separately and see if they are actually equal. So let's look at the left-hand side first. AB plus CD. What is AB? Well, your AB is just W plus Z, right? And what is your CD? Your CD is just X plus Y, like that. So that's your left hand side. Let's look at the right hand side. Okay, your right hand side is BC plus AD, but what is each of them? Obviously, your BC is W plus X. Okay? Your AD is just Y plus Z. So as you can see, no matter you're looking at the left hand side or right hand side, there are X plus Y plus Z plus W. Right? We just need to rearrange things a little bit differently. We will eventually prove the fact that they are the same. So you can claim that the left hand side being equal to right hand side. And that's the end of the proof. And that's the end of the question. So that's it for today. I will see you guys tomorrow in the live lessons. Peace.